Hello. This video is a little bit of a mess. There are several mistakes I made when writing the contents of this video, and even though I say correct those mistakes out here, it's a little bit difficult to do it back in my footage. Nevertheless, I hope you enjoy this video and can learn a thing or two about my approach to the Riemann hypothesis. My references are provided in my blog post, link in the description below. The Riemann hypothesis is such a challenging problem, so let's state it. Let xi function be the function written above. It's quite complicated. The most complicated part is this Riemann zeta function, which is the sum given there for only real part greater than 1. So you can see there in the complex plane, we can look at all values strictly greater than 1. Remember that I is equal to square root of -1. Given all of this, the Riemann hypothesis states that all the roots of big xi are real. Big xi is given there, and we're shifting this onto a certain line, 1/2, and this is called the critical line. But are all of the roots there? That's the big question. This is such a big question that the Riemann hypothesis is an 150-year-old problem. Let that sink in. We know that trillions of the roots are real, but are all of them? That's the question that remains to this day. And there are many approaches to this problem, many of which I will not get into. But my approach is to look at determinants. Consider the following series for big xi. It's given in this way, and we're particularly concentrating on that gamma n term right there. It works a little bit weirdly with the two lines. And note that we can calculate the gamma n's with integrals. Now, theorem of Schoenberg, who's been at this for a very long time, implies that RH, if all of the minors of this matrix are non-negative. And notice that here we have constant diagonals there, and from gamma 0, gamma 0, gamma 1, gamma 1. And back there, that's called topos. An easier approach is that we look at all the leading minors. It's sufficient to look at them, and it's RH is equivalent to all the leading minors being positive. So what I mean by that, we can start at the corner with gamma sub 0, but we can also start at the corner with gamma sub 1. And when we start shifting with the shifted minors, it becomes non-trivial and we can't compute it very well. There is a new tool we can use, bi-orthogonal polynomials on the unit circle. It's quite a mouthful. I've kind of gone over it through here. This all basically means we have a family of polynomials, phi n and phi hat n, satisfying this condition from the integral from 0 to 2 pi of this following integral, including the xi function. It's a delta Dirac. And that means that it's 1 if I equals j and 0 otherwise. Given these, we can calculate the polynomials in terms of the minors. This is related to the trigonometric moment problem. And in general, there are families for each weight, big xi times e to the negative k. As long as the minors are non-zero, required for RH, but I don't know how to prove this. And there's no easy formula for non-analytic functions, and that's why it's so hard to compute all of these. But there's a shining hope. We have a recurrence formula, if again, minors are non-zero. We have this very nice identity we can write here. Let it play out. But the gist of this is we're using the formula of determinant and the fact that we can express the gamma of n's with Fourier series. Now I'm excluding the trivial factors of 1 factorial times 2 pi to the n because they're positive. They won't affect the positivity. I'm ignoring them. Now, an example of some non-trivial debts written in terms of BOPUC is given here. And there's a -1 exponent that should not be there, but everything else is correct. And that alpha term is called a Jablonski coefficient. And that's equal to phi hat of n at 0. And that's the big formula. We can generalize this identity further to look at the non-analytic weights, which are necessary to examine the Riemann hypothesis. And down there, ignore the cap in the denominator, but the definition is correct. We have a generalized alpha of k and n. I'm used to writing r there, but ignore that. And we're generalizing the polynomials so that they correspond to weights of different non-analytic weights. We have a recurrence relation given there, and we can generalize it as I'm writing there. And through the previous relation, we can actually derive a recurrence relation for the Toeplitz determinants. And so I'm just writing out the identity here. These are calculations. I'm not sure what else to say. On it goes, and again, ignore kappa in the denominator. It actually ruins the calculations if it's down there. But what I want you to see automatically is that we have this -1 to the n. Two terms of that, just by exponent rules, those actually cancel out. There's no sign difference there. And that makes the formula a little bit more pretty to see. And then we're looking at the difference of these kappas. Those are really interesting. We'll get to them later. But those are related to the so-called iterated Turon differences. And the key thing about that is it's a very similar form to something called the Turon inequalities. Alright, I'm minimizing that just so we can get all the parts of the formula together. And I think this is the part where a lot of the formula struggles here. I think I'll correct it at the very end. This is not what my initial calculations look like, nor do I recommend you following this. Hope you can learn from my mistakes there. Oh, and in the process, I'm changing the k's. There's a lot to be done. I think I forgot the k's with those for Blunsky coefficients, but that's fine. I think I'm just doing everything to try to rectify the situation. And there we go. That should be squared. Perfect. Well, thanks to my notes. Well, no, why did I do that? Ignore taking that to the negative first power. Kind of messes everything up. Should be the other way around. I think I got confused with indices as well. But if you flip it around for that kappa there, everything is nice and rosy. We do have cancellations there. And if my calculations serve me correct, what we'll get at the very end is that we have two determinants on the left-hand side, and on the right-hand side, we have the Turon differences. As a satisfying implication, the Riemann hypothesis is true if and only if the first set of determinants is positive, and for all r or n, we have that these determinants down here, they satisfy the recurrence relation, and they're all greater than 0. I didn't make this explicit, but we can actually transform the quantity there into a function, and the condition that all of the Turon differences being positive is equivalent to this function being positive. This result comes from Sortis and Craven from, I believe, Jensen polynomials with applications. Just look it up on Google. It'll probably be an instant hit. All of that was a great start, but that doesn't even go into many of the details needed to actually prove the Riemann hypothesis, and I haven't gotten to everything. But nevertheless, thank you so much for watching, and remember, keep your curiosities wild and stay perpetual.